All right. Welcome to your Tarzan activity week. This is going to be the intro video, walking you through this, at least the start of this. So a suggestion that I have today before you continue is linked onto Planbook is this Tarzan activity. It looks similar to this. Also linked onto Planbook is this graph paper. And there is like a little mark on your graph paper, so sorry, it was the only one I had at home. We're just gonna have to deal with it. So if possible, it would be great if you could access this and even just have it up. You do not have to print it out. It's obviously slightly easier if you do, but if you look at the activity itself, it's just a bunch of questions, so there's no reason why you can't do this whole thing. It's 3 pages. There's no reason why you can't do this whole thing on a separate sheet of paper. What might be helpful to you is if you could print out this graph page. If not, any graph paper will do. You might just want to take a second if you could find a piece of graph paper and make the graphs look similar, or you can do that at another time. It's really just a blank sheet of graph paper that we pre-made graphs for you. So just a little heads up there. Might want to go handle that real quick before I get going. So this is going to be your Tarzan intro. As we have discussed with trig functions, they are used readily to explain periodic motion or to model, predict, analyze periodic motion. It can be used in anything where motion repeats itself. So we have looked, usually in this course when we're together, we will look at things like waves, Ferris wheels, a spring, how a spring moves up and down. Anyway, when we're thinking about our trig functions, of course, the motions that we're thinking about are those sine and cosine motions, where no matter where you start, sine and cosine create the same exact wave. It's just that one starts at 0 and one starts at 1, if you think about the parent function. And then also that crazy tangent function where you've got a periodic motion as it is approaching those asymptotes. So these are the periodic motions that we're going to be looking at and seeing which one applies best to our Tarzan problem. Now, the reason, not only are we going to be applying these trig functions, but we are also going to be revisiting the idea of rates of change. So rates of change have followed us this entire course. Most of our functions, we have looked at rates of change about those functions. We have looked at first rates of change. We have looked at second rates of change, which determine a great number of things, increasing or decreasing. They've determined concavity. And again, this is all just the precursor for calculus, and you will be looking at rates of change and rates of change in a more algebraic sense next year. So we're going to end our year very similarly. One of my favorite rates of change to talk about, and I'm just going to refresh your memory here a little bit, is about the ball lab. So the ball lab is, remember, going back to quadratics, where there was an initial height for a ball, which increases quickly at first with that initial velocity. And then as gravity starts to work, it slows down and slows down, approaches a velocity of 0. And then the velocity steadily increases, although negative, until it reaches the ground. So just as a quick little reminder, we also did this with our cooling lab. But this one is really kind of nice because, again, you have that quadratic function as our given. If you remember our rates of change, we're talking about how fast an output changes at a certain time. And if you do remember, I'm going to zoom in real close here. If you do remember, we can't determine how fast something changes at one point in time because there is no change. So the way that we go about that is we take a point just before and we take a point just after. And we are actually going to estimate that rate of change by finding the slope of that tangent line. So if we go back to this ball lab, the slope of the tangent line at first is positive, and it decreases over time, although it still stays positive. So we then, on the ball lab, we actually graphed this rate of change. So as we calculated that first rate of change using two-sided estimates, and we'll talk about this next time. We don't need to use two-sided estimates today yet, but we use two-sided estimates to determine the slope of the tangent line at that point, the average. And this was quite a large positive number. As we moved, as the ball increased in height, the rate of change slowed down over time. And while still positive, the rate of change was decreasing all the way until the ball reached its maximum height, which was exactly when the rate of change became 0. So what we learned then is that then our slopes became negative, negative, more negative, so negative, negative, more negative, and we were able to graph that first rate of change. And what we've actually found was that when we had our height of, depending on time, the first rate of change, this was a quadratic function. The first rate of change was determined to be the velocity. How does the height change over time? That's the velocity. This actually ended up being linear, a linear function, because that rate of change was constant. Well, then we could calculate the second rate of change. The second rate of change, the slope of these tangent lines was a negative, and it was exactly the same as that ball traveled. And we then determined the second rate of change, and I'll make a little graph here. It was a negative number, and it was actually negative 9.8. And what we remembered there is that this is actually acceleration due to gravity, which was a constant. So your very first exposure to this, you did an activity where you looked at the height of a ball over time, what happened to the velocity, and then the rate of change of the velocity. So we're going to do something similar with the Tarzan activity, except that we are going to be looking at, first of all, determining a best model for our Tarzan activity, and then, of course, starting to look at the rates of change and rates of change. But that will be for next time. So part 1 is simply to model a situation using a trig function, and we're going to choose one of them. So if you take a look at this activity, you will see that why we call this the Tarzan activity is that we are modeling the periodic motion of Jane as she swings back and forth on a vine over a croc-infested river. So we are going to assume that this is over a short period of time so that gravity doesn't start working its course. We know that the furthest out she swings is 50 feet from shore, and her closest distance to shore is going to be 20 feet. So at this point, she's pretty far away from safety. We know that it takes her 8 seconds to swing out and back. So first of all, let's just get a picture of what this looks like, and you're gonna have to just bear with me here as I draw my tree. So here's my tree. This is actually one of these moments where I'm like super excited that we're not in school because I'm not an artist. So there's our tree. And we know that Jane is, so I drew a terrible tree because Jane, here's the river. The tree is right next to a river. Maybe it's kind of, I don't know, partly in the river, who really knows. And then there's crocodiles down here, so I don't know how to draw a crocodile. Like, there's a mouth. I'll just draw a bunch of mouths, a bunch of scary crocodiles. And Jane, of course, is swinging back and forth, but she's not even getting close to shore, which means this tree needs to be more like I don't know. There's a branch. Let's say there's a big branch coming off of that tree there. Big branch. And let's say that Jane was escaping something and then she jumped off and grabbed the vine and now she's swinging back and forth. Okay, whatever. Ignore my tree. So Mr. Burgess could have done a much better job, but he's not here, so fine. All right, so here's Jane and she's swinging. And let's say that her particular vine that she has chosen, the closest that she gets to shore is going to be, so let's call shore, I'll get another color. Let's call shore 0. And the closest that she's going to get to shore is going to be 20 feet. So she is quite a long way from safety. So I'm going to bring this down here. So that's going to be 20 feet is the closest that she gets to shore. And then, of course, she swings. So here's her swinging. Whoa, that's super close. So here's her swinging. And she ends up, and the furthest away that she swings from shore is going to actually be 50 feet. Wow, that was a pretty good drawing, actually. It makes up for my horrendous tree. 50 feet from shore. So this point here is going to be 50. Okay, and we also know that it's going to take her 8 seconds to swing out and back. So 1, 2, 3, 4, 7, 8. All right, so if we were to actually add a little bit more information, and maybe that would be helpful, you know, the more you can conceptualize, the easier this is going to be to transfer to a mathematical application is, let's say, what do we know? Okay, well, let's call time 0 the second she grabs onto that, the second she starts her swing. So let's call this time equals 0. Okay, and we know that if she goes out and back, she's back also at time equals 8. So she's going to travel out. As she travels out, if she comes out and back and she's back at 8, well, then when would she be all the way out at 50? Well, she'd be all the way out at 50 after 4 seconds. Okay, so she's traveling out. So as she travels out from 0 to 4, that means that at a time of 2, she's halfway, which would put her where? 35? So this puts her at 35. It's getting kind of messy. It's all right. She continues, time of 4. All right, now let's say she's traveling backwards. So when else would she be at 35? Well, 2 more seconds, so that's also 6 and then 8. All right. Okay, so now we have our situation according to our givens, the information that we know. So this is going to be periodic motion as her distance increases and then decreases, and then let's assume it happens again, increases, decreases. Who knows for how long? She's dangling up there without her periodic motion being changed. And again, for our purposes, we're making sure that that's a constant motion, however it is that that's going to happen. All right, so the first thing we need to do is take this out of an application problem and turn it into a mathematical situation. So step 1 says make a graph that gives Jane's horizontal distance. All right, we already thought about that. As a function of time. Make the graph for 16 seconds. Okay, so it looks like she's going to do that twice. So the first thing that I'm going to do is I'm going to make a table. Okay, well, the two things that we're mapping is going to be horizontal distance and time. So which depends on which, time and then distance. All right, so I'm going 0 to 16 seconds. I already have my important points here. It looks like about every 2 seconds I need a value, which means that I'm going to go 0, 2, 4, 6, 8, 12, 16. That looks good to me. We've already kind of thought about this. At 0 seconds, she is going to be 20 feet from shore. After 2 seconds, she'll be at the bottom of her swing, and that's going to be 35 feet from shore. After 4 seconds, she's at the top of her swing, 50. And now she starts to travel back. So she's back at 35, back at 20, and now the process repeats itself. Or again, that periodic motion. And now she's back to 20. Okay, so table of values. We've just taken a pre-calculus concept, we've made a table out of it, and now we've got ourselves an Algebra 1 problem, which is always my favorite, which is just graph a simple table. You can use any old paper you want. If you have graph paper, ideal. If you have printed out the accompanying graph paper, even better. But again, if you just have a blank sheet of paper, you're fine, you're good to go. We did a bunch of trig functions on blank sheets of paper, so you should be fine. We like these because this really helps us to determine our rates of change and our rates of change, but again, unnecessary in these different remote learning times. All right, so here we go. I've got my times. Of course, because this is teacher created, they're going to go every 2. So I've got 2, 4, 6. What am I doing? That's not going to work, is it? I've already gone out way too far. All right, people, you're going to have to bear with me because I only have one of these graphs at home. I only need to go up to 16. I can just go by ones. That's way better. I know. Are you mad at me? I'm sorry. You'll get over it. Moral of the story is use pencil. Come on, Miss Moore. It's not my first rodeo. Moral of the story is also everyone makes mistakes. All right, so there we go. I'm going out to 16. That's way better. You could have gone by 2s, but again, the more that you can use your scale and change that appropriately, the better. All right, so I'm going to double check this as I go increasing. The furthest away from shore she needs to be is 50. I'm looking like I can go by 10s. I'm going to do a quick double check. 10, 20, 30. Okay, I'm good to go. 10, 20, 30, 40, 50. And again, this is distance depending on time. And we know that time is in seconds and distance is in feet. Okie dokie. All right, and now it's time to plot points from our table. So I've got my table right here. At 0, she is going to be up at 20. After 1 second, I have no idea. But after 2 seconds, I do know that she will be 35. 4 seconds, 50, 6 seconds, 35, 8 seconds. Okay, and there's 1 round. And the process repeats itself. Okay, I'm just double checking as I go. I'm sure I'll make a mistake, but trying not to. 16. Okay, so 2 periods of her swing. I think I did that right. All right, looks pretty good. Okay, so as you know, from swinging, she is going to be, as I move from 20 up to her peak swing, and you just know from a swing, I'm going to look back at my picture here. How are we going to connect these? When you swing on a swing, is there a constant motion that is created between the back of your swing and the front of their swing? Absolutely not. That's not a linear function. So you know when you swing, you start off slower at first, and then you speed up and you speed up and you speed up and you speed up and you speed up, and then it goes slower as that gravity works on you, and then you reach the top of your swing, and then the same thing happens. So at first, her distance is not going to be changing very fast. She starts off slowly at first. Slowly, 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 slowly. And now as she's picking up momentum, she starts to go faster and faster and faster and faster and faster. So right there I am at 35 seconds. And now after 35 seconds, I'm starting to increase my height, which means that now I'm flying, but as she reaches that top of her swing, gravity is going to start acting upon her, much like the ball, and there she is at the peak of her swing. Now, she's going to change direction. So if you have to change direction, that means that you're going to basically stop, and her distance is going to start getting going back, going back, going back. Wow, she's flying right now. Flying, flying, slowing down towards the back of her swing. And then the same thing repeats itself as you think about a swing. Okay, there we go. Okay, so now we have a graph of Jane and her distance over time. So now I'm going back here, all right, make a graph, check, did that. Next one, find a trig equation. Oh, so now we're looking for one of our trig equations. So we're looking sine, cosine, tangent. That gives Jane's distance over the river as a function of time, distance away from shore. Make sure that your function gives the values that you graphed. Okay, so from what you guys know about trig equations, we're looking for sine, cosine, or tangent. I think we can all agree that this is not modeling a tangent function. There are no values, there are no time values for which her distance does not exist, which means she's not going to end up with those asymptotes. So now I'm looking at this and I'm thinking to myself, yeah, for sure, sine or cosine. As we discussed at the beginning, it just kind of depends on where you start. So if we look at this a little bit, I think when you look at sine or cosine, we need to determine that midline. So if you look at this function and you talk about the wave, this midline has definitely been translated from 0 vertically. So this is kind of a tricky piece, is trying to come up with this equation. I'm going to walk you through this one, but then as this activity continues, you're going to be on your own to find the next. So if I think about this midline of 35 feet from shore, that means that my original sine or cosine has been translated up. So I'm going to start thinking about a couple things. One thing I know for sure is that this is a vertical translation up 15. No, 35. Sorry. Jeez. It's going to be late in the day. All right, we got a vertical translation up 35. That is going to affect our function that we come up with. Another thing we can tell now about our wave is we can tell the amplitude. So the amplitude, remember, is going to be the height of the wave from the midline. So from 35 to 50, this height is definitely 15. This negative height is 15, okay. So now we know that our amplitude is going to be 15. Okay, what else do we know? Well, now let's think about the period of our function. Well, how long does it take her to get there and back again? We already decided 8 seconds was the period. Okay, but period for sine and cosine is 2 pi. So we need to get from 2 pi to 8 seconds. So this is going to be a little trickier than any we have done before. This is the toughest part. If we were in school, in the classroom, I mean, I'd be walking around answering yes or no questions and you would be frustrated. But we're not, so here we go. You're going to start with 2 pi. You need to figure out how you're going to scale change that 2 pi. So you are going to multiply by, I don't know what, some sort of multiplier to get you to 8 seconds. Because if we lay down a cosine or a sine function, your reader is going to assume that you're going to have a period of 2 pi unless you tell it otherwise. So I need to figure out what that multiplier is going to be in order to get you from 2 pi to 8. Well, let's undo that, multiply by 2 pi. 2 pi's divide out, divide by 2 pi. So I actually end up with a multiplier of 8 divided by 2 is 4. My multiplier is going to be 4 over pi. All right, important. So we have our translation, we have our amplitude, we have our period, or what's going to change it. Now we need to determine if this is going to be sine or cosine. So when I look at this, I know that sine starts at 0, ends at 0. So we could use sine, or you can see that this one starts down the amplitude, which means that kind of reminds me of cosine, because cosine usually starts up and ends up, but that would just make it cosine reflected. So I'm going to say we go with cosine, and we just need to make sure that our amplitude is an amplitude reflected, so that it's starts down there at 20. All right, so here we go. Give it a title. You know what? I'm running out of space, so I'm going to go up above. So I'm going to say distance from shore as dependent upon time is going to be, all right, that amplitude is going to come first, negative 15. Now I've decided I'm going to use my cosine. All right, now as you know, I'm going to have my t value, but inside is where we're going to affect the period. So we know that our period needs to go from 2 pi to 8. So we need to multiply by 4 over pi in order to get from 2 pi to 8. But if you need to multiply by 4 over pi and you throw this transformation inside, this then needs to be pi over 4. Inside input inverse. All right, done. And now we need to move that whole function up 35. So let's throw a nice up 35 right there. Okay, so we've got our graph. We've built our function. It's kind of tricky building functions from graphs. You worked on a couple of those, I don't know, last week sometime. But there you go on that one. So that's number 1 and number 2. Your assignment between now and the next time I see you, or now in the next video that you watch, is we would like you to try to do numbers 3 through 7. So these ask a bunch of questions about velocity. When will her velocity be the greatest? When will it be the largest negative? And just kind of asking you to analyze the situation 3 through 7. Shouldn't take you too long. We'll see. Okay, that's all we got. Next time I see you, I believe I'll be walking through those answers and talking that through and then taking you on to the next step. See you later.